Okay, here we have a short video about the vectors and the dot products. Previously, we talked about some of the operations that you can use with vectors. We can add them, we can subtract vectors, we can multiply vectors by a scalar multiple, but can we multiply a vector by another vector? And it turns out we can, and by this definition, this is what we're going to use. The dot product of u, which can be represented in its component form of u1 and u2, and v with its component form of v1 and v2 is defined as this. Here we want to take the first component of vector u and we want to multiply it by the first component of vector v, which gives us whatever the product of u1 times v1 is. And we're going to add that product to the second component of u with the second component of v. That's what we get from here, which this will end up giving us a scalar, some type of number. Okay. Dot products also have their own properties, which kind of align with our properties that we're used to in today, like the commutative property. Like the order doesn't matter. It doesn't matter if you do the dot product of u and v, you're going to get the same answer as the dot product as v and u. We know with our numbers that if you multiply by 0, then the product of itself is going to be 0. But here we have a bold-faced 0. That's the 0 vector. If you multiply by any given vector, that its dot product will always be 0. Similarly, we can think of vector multiplication like distributive property, where we can take the outside vector and just distribute it through, and then we can get the two different dot products and add them up together. We can take two vectors and multiply it by itself, which ends up being the magnitude squared, and we'll come back to that in a little bit later in this video. And third, if we take a dot product between two vectors and we want to multiply it by some type of scalar, we can take the scalar that we have here and we can either multiply it by one of the vectors and then do a dot product, or we can take that scalar and multiply by the other vector, and that will be equivalent. But first, we're going to go in and just find some dot products. So we want to take, by our definition, the first component of the first vector and the first component of the second vector, and we will want to multiply them up. So we're going to do 4 times 2, sorry. We're going to add that product to whatever 5 times 3 is. Well, 5 times 3 we know is 15, so we are simply taking 8 plus 15, which gives us an answer of 23. So the dot product between these two vectors is just a number 23. Jumping over to example B, we are going to take, again, the corresponding components, 2 times 1, first, and then we're going to add to it whatever negative 1 times 2 is, and we get a 2 plus negative 2, which gives us 0. And a little bit later on in this lesson, we're going to find out that that actually has a significant meaning to us. And one final dot product, we could take 0 times 4, and then add that to whatever 3 times negative 2 is, which will give us 0 plus negative 6, which is simply the number negative 6. So that's finding dot product and using the dot product definition. Well, we want to be able to use some of the properties that we had from above here in this list along with finding dot product, so we're going to look at some examples there. One way that we will look at these properties is I want you to think more along the lines of PEMDAS. We learned the order of operations that we would work with parentheses first. We would then want to do any exponents. We're not really going to have many exponents here, but however, do some multiplication afterwards and so on. So what I'm getting at is that I want to do u times v first in example A, and just to make this a little bit more corresponding to u, I'm going to give these vectors some colors. So I'm going to let u be red and v be blue, and I'm going to do the dot product between u and v first before I even worry about the vector w. So I go through that and I take those components. I want to take negative 1 times the 2, and then I want to take the 3 times the negative 4 and figure out what that dot product is, which will give me negative 2 plus negative 12, which is just negative 14. It ends up giving me some type of scalar number. What I'm going to do with that number then is I am going to use what I know about scalar multiplication, or in other words, basically distributing this number through the vector that we had for w, which is 1, negative 2. Well, 1 times that negative 14 gives us negative 14, and then negative 14 times the negative 2 gives us the 28. So this dot product multiplied with another vector gives us another vector, which is negative 4, 28 in its component form. Okay, going on to example B, This time we're taking a dot product between a vector and then a scalar multiple of a vector. So I'm going to first figure out what's the scalar multiplication of 2 times v. So here I will go ahead and just distribute the 2 through. Now 2 times the 2, and then 2 times the -4, we've got a new vector of 4, -8 that we're going to find the dot product with the red vector. So now that I bring in that red vector, I can see that I can take my -1 times the 4, the 3 times the -8, and get a new dot product. So here we have -1 times that 4 and the 3 times the -8, like I said, which will give us -4 minus 24, and its dot product will give us -28. The last example I'm going to look at is finding the magnitude of u. Well, instead of using our old definition of the magnitude, we're going to look at one of the properties that said that, well, the magnitude of a vector squared is just the vector times itself. I'm going to go ahead and multiply the red vectors by themselves and do their component forms by each other to find its dot product. But when I'm doing this, what I'm really doing is finding the magnitude squared. So just keep that in mind. -1 times -1, add it to whatever 3 times 3 is. 10 is what the magnitude squared is. We need the magnitude itself, so of course we're going to just square root that number, and then we'll of course have the magnitude of the vector in its form. So that's one way that you could find the magnitude without doing the old magnitude equation. So that's using the definition of dot products and some of the properties of dot products.